workshop. The first talk will be by Sanjoy.
Okay, so I'll be talking about nearest neighbor, which is one of the oldest and most well-weathered and most widely used forms of information retrieval and classification. And just to give you a quick example, you take a photograph of a bird you've never seen before. You give it to your computer, and you ask the computer, what is this thing? And the computer has got some vast database of images, all of which have got some annotations associated with them. And it just finds the closest thing and said, oh, it looks like this, which is a warbler or something like that. So in order for this to work well, what really matters is having a very good representation. And this is something that the vision community, for example, has been improving by leaps and bounds over the last 2 decades. So representation is key, but I'll be talking about two other aspects of the problem, which is statistical analysis, what is the error rate of a nearest neighbor classifier, and the algorithmic side, which is how do you find a nearest neighbor quickly. Okay, so in terms of the rate of convergence of nearest neighbor, so let's just say we have points from some distribution in p-dimensional Euclidean space. And each point has a label that's possibly stochastic. Okay, so the labels are binary, either 0 or 1. And at point x, the probability of getting a label 1 is some eta of x. Okay, so very often a lot of the labels are deterministic. The parts of the space where it's definitely a 1, definitely a 0. Okay, so this person definitely has cancer. This person definitely does not, and this person, 50-50. Okay. So in terms of the classical theory for the classical statistical theory for nearest neighbor, the first question is, can we give an error bound on nearest neighbor? What is the error of the nearest neighbor classifier? That depends only on P and N. Like, can we say, oh, the error of nearest neighbor is like P over N or something like that? And the answer to that is no. And the reason for that is that this eta function, this conditional probability distribution, could be like this, could be like really spiky. And so the smoothness of this conditional probability function is really key. Okay. So then the next step is, okay, let's make a smoothness assumption, and the standard sort of smoothness assumption in this sort of non-parametric statistics is that some sort of Holder continuity. So for example, if alpha equals 1, then this would be a Lipschitz assumption. And later I'll explain why this is really a very bad sort of assumption for nearest neighbor. It doesn't fit the problem at all. Okay. But under this, then you get this error bound. Okay, you said, okay, well, if you have n points, this is the error rate of nearest neighbor classification. And at that point, it's just like gulp. It's like, because this means that it's exponential in the dimension. Okay, so if you want any sort of decent error rate, it looks like you need exponentially many points. And so if the dimension is 50 or more, there would be, or actually even a little bit less, there would be absolutely no reason to use nearest neighbor. Okay.
So
yeah.
One nearest neighbor, this will not converge to the base.
Right, so this is if you do k nearest neighbor for appropriate k. And so we'll spell that out a little bit. Yeah. And so so you might hope that this bound is loose, but then they tell you, no, this is actually an optimal bound. And why? Because there exists a distribution for which the bound is actually tight. Okay, and it's at this point that the theory really gets into the realm of complete absurdity, okay? So of all the countless possible distributions, right, there is one for which this bound is tight, and therefore it's optimal, okay? So, if this were really a picture of reality, then we wouldn't want to use this method, but fortunately it isn't. And so what we'd like is, for something, and something that's achievable for non-parametric estimators like nearest neighbor, is first of all bounds that hold without assumptions. And these are useful because then once you have the bound, it might not be pretty, but it really helps bring out what are the real parameters that govern the difficulty of the problem. Okay, so once you have a bound of that form. And then how do you know the bounds are tight? When the upper and lower bounds match on every instance. Okay, so we are interested in things that are really right for the instance and not. Okay, so then let's talk a little bit about nearest neighbor search. In this problem, you have the Okay, so now you have some vast collection of points, and you want to find the nearest neighbor. And brute force is linear in n, and which is really not appealing if you have a very large collection. And so, since at least the early 70s, people have been coming up with clever data structures to answer these queries quickly. And so, ideally, what we'd like is a data structure whose space requirement is just linear and whose query time is little O of n. And so, so for example, if the points were just on the line, this would be easy. You just sort the points, and then when you get a query, you do binary search, and so you would just get linear, and you'd get log n. And then you'd hope that, okay, so once we go into higher dimension, maybe we can do some sort of generalization of this, like 1D binary search. And some of the data structures have that flavor, but unfortunately, these generalizations tend to be exponential in the dimension. These generalizations work out to be exponential. And so here's just a sort of a troubling example. If you're in p-dimensional space, then you can find 2 to the p points that are roughly the same distance from each other, almost exactly the same distance. And so if your endpoints are drawn from these, and your query is also drawn from these, then it does seem like you're in somewhat of a difficult situation. Now, I haven't seen a sort of a lower bound that's been formalized of this type, but nonetheless, it's something that, just something that gives one pause. Okay? So one really beautiful line of work that's been done has been on approximate nearest neighbor, where you say, okay, well, nearest neighbor sounds difficult. What if we just want not the nearest neighbor, but anything that's at most c times as far away as the nearest neighbor? What if we just do that? And there was this work started by Piotr Indyk and Rajiv Motwani, and more recently taken up by Alex Andoni and others, where they show there's this beautiful framework, locality-sensitive hashing, that in Euclidean space lets you get roughly these parameters. Okay, so you get a data structure. For example, if you want 2 approximate nearest neighbor, you get a data structure of size n to the 1.25. Okay, so more than linear, but not too bad. And you get a query time of n to the 0.25, which is good. Okay, and this is very successful in practice. Works well. Now, on the theory side, one sort of odd thing about these bounds is, is C really a good measure of the hardness of the problem? Is it really capturing, the difficulty of instances? It seems like a C approximation would mean very different things for different point configurations. Okay, so for example, let's just look at the standard MNIST data set that is used in the introductory machine learning classes. This is considered an easy data set, 60,000 images of handwritten digits. How does nearest neighbor work on this? Okay, so let's look at, for example, C equals 1, which is the actual nearest neighbor, and that has an error rate of 3%. What if we look at 1.2 approximate nearest neighbors and pick one at random? Okay, so lots of them, pick one at random. The error rate goes up to 9%. And once you get to 2 approximate nearest neighbors, pick one at random, the error rate goes up to 51%. Okay, so this is a case in which you'd say, okay, well, I really need C to be tiny, like 1.1 in order for this to fly, which means you get a quadratic data structure size and the search time is almost linear. Oh, maybe I shouldn't use locality-sensitive hashing on this thing. But actually, locality-sensitive hashing works fantastically well on this. And not just C approximate nearest neighbors, it has a good chance of finding the exact nearest neighbor. Okay, so there's something, so what's happened, I think, is that these bounds are, it's very impressive that a bound can be given like this, but because they have thrown away all parameters that actually govern the difficulty of the instance, they are necessarily somewhat loose. Okay, and so.
Could I say?
Yeah.
A comment. So, I think for MNIST, all kinds of things work, right?
Right.
And it's not completely clear why, but I mean, there's also like the random kitchen sinks, right? Like random Gaussian filters, that's a reasonable feature. So there's all kinds of things going on with MNIST, which.
Right. So it might be specific to this example, right? But actually, I think it's a more general phenomenon. We do a lot of experiments with these methods, and it finds the exact nearest neighbor more often than you would imagine, for example. Okay. So I'll talk about 2 sort of results, one having to do with nearest neighbor search and one to do with nearest neighbor classification, and both where we are looking for sort of instance optimality. Okay? Now, in terms of nearest neighbor search, the sort of the two games in town, as far as I can make out it, there's the hashing methods and there are the tree-based methods, and they both work extremely well. And so I'll be talking about the tree method, since those have been analyzed a little bit less. Okay? And the mother of all tree data structures for nearest neighbor is the KD tree. Okay? So this is in Euclidean space. You have your endpoints, you put a box around them. And then you pick a coordinate direction and you split it in the median. Okay? So you have 50% of the points on one side, 50% on the other, and then you recurse. Okay? So you have 1 million points, and you're going to 500,000, 250,000, and you stop when the leaves have, say, 1,000 points each. Okay? And that's when you stop building the tree. Now a query arrives. So you take the query, you go down the tree, and you get to a leaf with 1,000 points in it, and you look for the nearest neighbor amongst those 1,000, and you say that's the nearest neighbor. Okay, so for example, let's say the query lies over here. You would go down into this box, and you would say, oh, the nearest neighbor is that point. Now, of course, that's not the nearest neighbor, but that's what it says. Okay, and so it might not give you the right answer, but it's certainly fast. Okay, which is a virtue. Now, one thing that people have done a lot is to look for ways to sort of reduce the failure probability of this method. Okay, and there are two things. So method number one is to use randomization, and so for example, to pick directions uniformly at random from the unit sphere. Okay, and at first glance, this seems like a bad idea, but I'll just explain in a second how it's actually used and why this works well, okay? And the second is to allow cells that overlap a little bit, okay? So in terms of the data structure of this form that I think is probably would be considered, the one to use these days, it's forests of randomized trees. So once you randomize the tree, you get something like an LSH data structure. And just like in LSH, where you take multiple copies of it, you do the same thing with the tree. So you get a forest of them, and then the error rate just goes down very fast. And these are super popular data structures. And so we were interested in analyzing them. Okay? So what are the two things that are going on? So the first is that you pick a direction uniformly at random from the unit sphere, and then you split at the median. We'll look at a slight variant of it, where instead of splitting at the median, you just pick a random percentile. So you say somewhere between 25th percentile and 75th percentile, pick a number at random, let's say 60, split at the 60th percentile. The second thing is to have overlapping splits. So in other words, to have a buffer zone in the middle where the points go both ways. Okay, so the bad case is where your query is here, and you split at the median, and it gets separated from its nearest neighbor. So right now, I'm only going to be talking about exact nearest neighbor search. Okay, so it gets separated from its nearest neighbor. So to kind of reduce the chance of that happening, what you say is, okay, look, the top 45% of points is only going to go to the left. The bottom 45% will go to the right, and the middle 10% will go both ways. Okay, and so the data structure becomes slightly superlinear. Okay, and now when you get a query, you just go one way. So if the query is over here, you only go to the right. If it's over there, you go to the left. Okay, so the query time remains unchanged. But the data structure is a little bigger than before. So for example, if you have a 5% overlap, then the data structure size goes up to n to the 1.16. Okay, so it becomes higher. So these are the things we want to analyze. And so you have the original KD tree, which is not that great. Then you have the random projection tree, where the direction is chosen at random, and the splits are perturbed. There's this perturbation. And then you have the thing with the overlapping splits. Okay? And it turns out that roughly the same bound holds for both of these. So I'll be talking about the spill tree, but roughly the same thing holds for the other one as well. So the interesting thing is that you can give a bound that makes no assumptions about the data. Okay? So pick any data set you like, x1 through xn, any query you like. Okay? And now let's imagine that we have ordered the points by their distance from the query. So x1 is the closest point, xn is the furthest point. The probability of failure depends crucially on this quantity. Okay, I'll go through the argument in a second, but you'll see that this is both an upper bound and a lower bound. I mean, this is approximately tight, except where there's a lot of collinear triples. Okay. So what is this? So it's the distance to the nearest divided by the distance to the second nearest, plus the distance to the nearest divided by the distance to the third nearest, and so on. So for example, if the nearest neighbor is very close and everything else is very far away, this is basically 0. And if everything's the same distance, this is 1. Those are the two extremes, okay? And everything else lies somewhere in the middle. So this is sort of the potential function, or this is really what controls the search time of this data structure. So,
So which data structure again?
sorry, this is for either of them actually, the spill tree or the failure probability. Sorry, so this is what controls the failure probability of this, okay? So why is this? And the argument is super simple, so I'll just go through it in its entirety.
So we need failure to find the nearest neighbor.
Correct, yeah. Failure to find, so we want x of 1, and we want to know what's the chance that you get something else back, right?
So it does not depend on the overlap alpha that you have?
It will, but that'll just be a term in front. So I'll give the proper bound in a second, but this is basically the difficulty parameter, if one had to pull one out of the problem, okay? So what can go wrong? So the only thing can happen is that, so at each point you're splitting the points, and if the query gets separated from its nearest neighbor, initially they're together at the top, if at some point they get separated, that's when you're in trouble. And so at each step, you're picking a random direction, you're projecting everything onto that direction. The query goes there, the nearest neighbor goes there. The only way they can be separated because of the buffer zone is if a lot of points fall between them. Okay, a huge number of points, basically. So to analyze that, let's just look at the case of 3 points, first of all. So you have the query, you have the nearest neighbor, and this is some other point, okay? And this point is a little bit further away, and what we want to know is if you pick a random direction, what's the chance that this point is going to fall between these two? What's the probability of that? And so the main thing is this is just a two-dimensional problem, okay? Because you can make Q be the origin, and then you just look at this, make this the origin, look at the plane defined by x and y. And so there's the plane in which these things lie. And now the direction you're picking, of course, are going to stick out of this plane, but all that matters is the projection of the direction on that plane, okay? And if it's a uniform direction overall, then it's also a uniform direction within the plane. So it's just a 2D problem, right? Okay. So this is our query. This is the nearest neighbor in some other point. Let's say we pick this direction over here. If we pick a direction like that, we're good because y is out here and x is over there. So now let's move the direction clockwise. This is the first place at which we run into trouble, the perpendicular to the line connecting x, y. Because at this point, x and y, if this is the direction, x and y actually fall onto the same point. So this is the first place at which we run into trouble. Now we keep going. These are all bad angles. If you project over here, then y falls between x and q. And this is the last one at which you run into trouble because y falls on top of q. Okay, so there's this bad angle, and the probability of falling within that angle is just theta over 2 pi. And what is theta? Well, this is just high school geometry. It's like similar triangles and sines and cosines and stuff like that. Okay, and once you plug that stuff in, you see that the probability of this happening is the following. It's a half times the distance to the nearest neighbor divided by the distance to the other point. So if they're equidistant, then the probability is a half. And if this is really far away, then the probability is small. So it's just that ratio. And this is basically tight unless the points are highly collinear or almost collinear. So this is for 3 points. And of course, we actually have n points. So this is the query, this is the nearest neighbor, and we want to know what fraction of these n points are actually going to fall between these. So we're picking a direction at random. What fraction of these points are going to fall between q and x1, okay? And if that fraction is large, like greater than alpha, that's when we are in trouble, okay? Well, the expected fraction is easy to compute. It's just this thing, the thing we were actually calling a potential function just by linearity of expectation, okay? And so that's the expected fraction. What's the probability that the fraction is greater than alpha? That divided by alpha. It's just Markov's inequality. Okay, so we get. So we know that we know what the probability is that we're going to run into trouble at the very top level of the tree. Okay. Now things change a little bit at the second level because at the top you have all million points, and then the next level you just have 600,000 of them. Okay. Which 600,000 you don't really know. Well, the worst case is the 600,000 that are closest to the query. Okay. And so let's look at a situation where we have just m points, where we just write the same sum, but for the m points closest to the query. And then we sum that down the tree. Okay? And so we're done. So it's very easy. And this is the error probability then. Okay? We've just summed over all levels of the tree. So I equals 0 is the top level, then the second level. Okay? And and we just write out the same term at each level, okay? So this is the thing we need to bound. This is the thing that controls really the performance of this data structure. And we need to bound this. Yeah.
So you were doing the computation based on expectations, but like things can be very much correlated. Let's say it could be that either all points are between or none of them is between. Let's say all points except the nearest neighbor are essentially at the same place. So, and in other cases they're very spread out. So it doesn't seem like expectation alone should really tell you the story.
Right. So what we have here is an upper bound. What's not clear is that so the expected fraction is this. We have, in order to bound the chance that it's greater than alpha, we just divide by alpha, and we're just taking a union bound over the levels of the tree.
You said that you wanted a bound that is tight, so that's not a tight bound.
Right. So it's not.
Just an upper bound.
That's true. So the part that's not tight is the alpha and the sum. The part that is tight is the expression itself, right? So this is
The expectation is tight.
right. Yeah.
This is not the bound. The expectation is just a method of getting some bound.
Right. Yeah. So for this method, it's clear that this is sort of the difficulty parameter, but exactly like what the dependence on alpha is, for example, is or the number of levels is unclear. Right? Yeah. So we'll just focus on bounding this thing and then plug it into the bound. And the case I'll look at is sort of a, so intuitively it sort of makes sense, but we do want to like instantiate this bound for one interesting case at least. And so I've looked at a few, where the data have cluster structure, where the data come from a topic model, and so on. One interesting thing to look at is the case where the data have bounded doubling dimension. Okay, so this is a notion of intrinsic dimension that was introduced by Gupta, Kraut-Kramer, and Lee, because I think they wanted a sort of a non-asymptotic version of Aswad's dimension. And so what this says is that you have this point set, and the way we're going to define its intrinsic dimension is we say, look at balls, look at any ball, look at the points that fall in that ball. How many balls of half the radius do you need to cover those points? Okay? So for example, if your point set is a line that's embedded in some super high dimensional space, the doubling dimension is 1, because if you look at any ball and you look at the point part of the line that's inside the ball, you need 2 balls of half the radius to cover it. So the doubling dimension is 1. Okay? And so this also generalizes a k-dimensional flat, that's doubling dimension O of k. Manifolds, if you have a manifold of bounded curvature, then it has neighborhoods of width proportional to the curvature that also have doubling dimension O of k, and generalizes sparse sets. And so for doubling dimension, you can show that, so I'm not going to go through the entire argument. I'll just give some sort of high level, remarks. But basically, what you need to do is to grow the tree until the sizes of leaves are about k to the k, where k is the doubling dimension. And so you get a query time that's roughly k to the k plus log n. Okay? Now, a similar query time, this sort of exponential dependence on k and then the log n has been obtained for lots of other data structures. Okay? So the real difference over here is that this is a data structure, that's quite widely used and had not been analyzed before, and so it's of interest to see what it does. So how do we bound this term, given only the doubling dimension? I won't go through the whole argument, but basically, so here's a very basic question that keeps coming up again and again in nearest neighbor analysis. Okay, and the question is this: pick any endpoints in p-dimensional space. Okay, and take one of those points. Let's call it x. How many of the remaining n-1 points can have this as its nearest neighbor? Can they all n-1 of them have this as its nearest neighbor? Okay, so that's the question, right? Yeah.
Do you need the RP assumption or just the doubling dimension metric in general?
Yes, I'll get to that in a sec. Yeah, we don't really. And so I believe this was shown by Stone in the 70s that is basically at most 2 to the p other points, or maybe it's 5 to the p other points, can have this as its nearest neighbor. Okay, and the argument that he used He was trying to show the universal consistency of nearest neighbor, which is the topic I will get to next. But so the argument he was using was he was saying, let's look at a bunch of cones, like really narrow cones, subtended at this point x. Okay, and let's just cover space with these cones. Okay, these cones are so thin that within each cone, only one point can have x as its nearest neighbor. Okay, so this point can have x as its nearest neighbor, but anything else would actually be closer to this because the cone is so thin. I think the angle has to be like 30 degrees or something like that. And so you get this cover by these very thin cones. And the cones have a fixed angle, so the number of cones you need is just like 2 to the d or 6 to the d or something like that. Okay, so that's the argument. And then it was shown more recently by Clarkson that you can kind of do something like this for doubling dimension as well. Okay, so if the doubling dimension is k, you can do something kind of similar with the doubling dimension. And then you can see how this would go naturally into this, because now we have all these terms that we want to bound, and then you can say, let's again do this covering of space by these cones, and how much can the points in a cone contribute to the sum? And so you do it that way. Yeah.
The doubling dimension is defined asymptotically as the size of the balls go to 0, right?
No, so doubling dimension is the non-asymptotic version, where it holds for all balls. Yeah, so it's not just as the scale goes to 0. That's right. And so that's what makes it so useful in like the more computer sciencey stuff. Yeah. Okay, so that's sort of a high level of the argument. So some open problems on the algorithmic front, I would say it would be nice to look at other, I mean, there are all these other sort of structures that we attribute to data, dictionaries, topics, what does this look like for those kinds of data? And second, is this a good predictor of when nearest neighbor, of which nearest neighbor problems are easier than others? So when I look at these nearest experiments comparing nearest neighbor methods, the interesting thing is never, is this method 2% better than that method? It's that look at these different data sets. On this data set, nearest neighbor works so well. And on this other data set, it just works so much worse. What is going on? What's the difference, right? So it's more like on the data side than the actual algorithm side. And so it would be interesting if this, for example, is sort of correlated with those sort of observed behaviors. Yeah.
So maybe it's a good time. Like this kind of like measures the complexity of the problem.
Mm-hmm.
And just as you pointed out, if you have different algorithms, and not only 2%, it doesn't matter that much. But can you, using this measure, can you distinguish between like good and bad algorithms? Just using this measure, right? I mean, assuming this is like the right gauge for the difficulty of the problem.
Yeah, so it would be interesting.
V squared or log or something.
Right. So it might be, so for example, maybe it's possible to go back and analyze the failure probability of LSH at finding the exact nearest neighbor. Okay, since it really does seem to, do a decent job at finding the exact nearest neighbor very often, right? Maybe one could just go back and analyze it, and maybe something like this pops up again. I don't know. That would be really interesting. Yeah.
When you said nearest neighbor works well, did you mean as a classifier, or did you mean as that these algorithms work well? Is there a correlation between those two things? That when it's good statistically, it's also relatively easy to ask algorithmically.
I honestly haven't the faintest idea.
We have lower bounds in terms of the Lipschitz, for example, it's a very good question, because the labeling function also affects your ability to predict, not only the search for a nearest neighbor.
Right. Yeah. So my guess is that the two things are actually unrelated, but so over here I'm just talking about its performance in actually finding the exact nearest neighbor, and but yeah, that would be interesting if there was some connection. Okay. Right. So now I'm going to get to the other side, which is the nearest neighbor classification, and okay. So here we'll move to a slightly more general setting. In the statistical theory of nearest neighbor, the whole game has to do with 5 minutes. Okay, I'll be quick. Has to do with generality. No assumptions, as general as possible. That's what it's all about, okay, in sort of this non-parametric estimation. Okay, so the data lies in some metric space, okay, And so we can look at one nearest neighbor, we can look at k nearest neighbor, we look at the k closest and you average, and actually we typically let k grow with n, like log n or something. Okay. So now we assume that there's some underlying distribution mu from which the points come, and at any value of x, the label is stochastic. The chance that it's 1 is some eta of x. Okay? And so the very best classifier is one that at point x you predict 1 if that eta is greater than a half, otherwise you predict 0. That's the best thing you can do, and that's called the Bayes optimal classifier, and that achieves the best possible error, which is r star, some r star, okay, whatever r star happens to be. And in general, this Bayes optimal boundary is something crazy, okay? It's some like really strange looking thing, okay? Nothing that we can hope to nail down with a finite data set, okay? And so we're going to be looking at the k nearest neighbor classifier based on n labeled points, which is some sort of hopefully discrete approximation to that boundary. And what we're hoping is that as n grows, this converges to that. Okay, does that? Okay. So what are some questions of interest? So one thing we'd like to do is to just bound the error of this. Okay, how much worse is this than that? And you know, following the methodology that I was espousing, we just like to give assumption-free bounds. Okay, so it might not look pretty, but it'll help you understand what controls the difficulty of the problem. Okay, and in this case, actually, it's pretty simple. Now, in getting bounds that look a little bit nicer, or a bit more interpretable, smoothness matters. And that's because, you know, having a distribution of y that looks like that, so this is x, that's y, the probability that y is equal to 1, eta, it's much easier than this because, you know, here you need to predict 1, 0, 1, 0, 1, 0. It's very jagged. So this looks like a harder situation than that. And so the smoothness of this eta function really matters. And what I'll show is that nearest neighbor really demands its own notion of smoothness rather than simply taking the stuff that, you know, is used for regression. And if you use that, you get upper and lower bounds that are qualitatively similar for every distribution in the smoothness class. Okay, it's not this sort of minimax thing where the upper bound holds for everything and the lower bound only holds for one item in the class. Okay, so they actually match for every distribution in the class. And then finally, I'll talk about consistency. So what we'd like is universal consistency. And universal consistency means consistency without assumptions. Okay? You're not assuming, for example, that eta is continuous or anything like that. You just, you know, no matter what the distribution is, it's got to be consistent. And that was shown in the 70s for Euclidean space by Stone. Like just a wonderful result. But those arguments actually don't generalize to other metric spaces. And it turns out that just by starting from this point and using a different kind of argument, which is basically just calculus, we get universal consistency in a much richer class of metric spaces. Okay. So let's see. So let me let me just talk a little bit about smoothness since I don't have much time. So how do we parameterize smoothness? The usual way to do this is this sort of Holder condition. Okay? Alpha equals 1 means Lipschitz. And then there's another thing that matters. So this just says that eta doesn't change too fast. Okay? The other thing that matters is that, so the boundary is really the points at which this eta function is a half. That's the points at which it's a toss-up whether the label is 0 or 1. It could be either way. And the points that are like 0.51 and 0.49, those are also bad. Okay? So let's look at this region around a half, a with t margin around a half, places where the eta is between a half plus or minus t. Okay? And we are hoping that this region has very low probability mass. Okay? And there's the Sibakov-Manman condition where it says, okay, the probability mass of these regions is at most some function. Okay? And so the classical bounds have been given in terms of these. These people showed that, okay, under these two parameterizations of smoothness, this is the kind of bound that is the best possible, and it turns out that nearest neighbor achieves these bounds. Okay. So the smoothness condition that I advocate, which is a little different, is the following. So for nearest neighbor, it does not matter how eta changes. So we want to know how much does eta change within this interval. We don't want to measure the rate of eta's change with respect to the length between x and x prime, but rather the amount of probability mass between x and x prime. And that makes a huge difference, okay? So instead of measuring how much this function eta changes in terms of distance, measure how much it changes by probability mass, because this is really the only thing that matters in nearest neighbor, okay? And so we get this other notion. We also use the same smoothness parameter, but now instead of distance, we've just plugged in probability mass, okay? And it turns out that if you do this, which is a simple enough thing, the bounds just become way cleaner, and you get upper and lower bounds that are really close on the distributions, okay? And it's a generalization of the previous notion. If it's Holder continuous, then it's also smooth in this sense. And so what do these bounds look like? It says that the failure probability for nearest neighbor for any distribution in the class is really just the amount of probability mass that lies within the 1 over square root k margin of the distribution. Okay, and so 1/2 plus or minus 1 over square root k, and that's really what matters, the amount of probability mass that lies in there.
This is margin around what?
This is margin, so the decision boundary is all points for which eta is exactly 1/2, and these are all points for which it's 1/2 plus or minus 1 over square root k. What is the probability mass of that region? And that turns out to be a good upper bound and lower bound. Okay, so unfortunately, I don't think I'm going to get to the universal consistency, but I'll just end with some open problems. So we were able to show universal consistency in a range of metric spaces, but not all of them. And so here's a very interesting question. Is there any metric space in which nearest neighbor fails to be consistent? Like, is it ever not consistent, and that's not known? Is there some sort of crazy metric space in which this method can
could
be
you say
shown?
what that would mean again? So just in words, like a metric space in which it fails to be consistent. What is
Yeah,
that?
so what we need, so consistency means that if you let k grow as a function of n, then the k nearest neighbor classifier converges to the Bayes optimal classifier. Okay, so, or rather the error rate of the k nearest neighbor classifier converges to the Bayes error rate, okay? So that holds for any distribution in Euclidean space, and we've shown that it holds for, a bunch of metric spaces. Basically metric, for example, doubling dimension bounded, or spaces that are directionally limited. But it still leaves open the possibility that there's some metric spaces in which k nearest neighbor is not consistent. Metric measure spaces, so it will also depend on mu. And so that's kind of an interesting question. And another question is, so this sort of assumption-free consistency or bounds in more general distance spaces. So the stuff that I just sort of went over very briefly relies a lot upon tools that were developed for analysis in metric spaces. And so if it can be generalized to some sort of even slightly more general topological spaces, then we could look at things like KL divergence and other distance functions of interest that are not metrics. Okay, thank you. Yeah.
So, okay.
Go ahead.
So there was somewhat of a disconnect in the worldviews in the first and the second halves of the. Do you agree, or?
They're just very different questions. One's the algorithmic, one's the statistical.
So in the following sense, right? So for the first half, the bad case is when there are lots of points which are nearby, right? Roughly the same distance. Whereas in the second view, right, where you think of the points being from a distribution, that's actually a good case. Because any of those points is probably equally good for decision making. Right?
So that would, yeah.
Right? So in fact, it's the wrong measure in the first half, right? I think the second half is roughly the correct view, right? And so the measure in the first half is not correct.
You're killing me. That was my question.
Yeah, so that would be cool if they complemented, if it turned out to be complementary.
We're just saying it in a slightly different way. the algorithmic question is not what's the nearest neighbor, it's what's the label of the nearest neighbor.
Yeah.
And so, you know, then the algorithmic complexity depends on the label function as well as the metric space itself.
And I'm suggesting that in the second view, you know, any setting where there are lots of nearby neighbors which are very close, you actually have a lot of confidence in what the correct label is. That's my suggestion. Whereas when there aren't too many close by points, you are in outlier land, and probably even if you find the nearest neighbor, it's not clear.
Yeah, that's a very interesting sort of question. So it'd be nice to figure out like what's the right way to formalize this thing. Yeah.
Yeah, I mean, I was about to ask the question in the first half, but I said, wait, I know Sanjoy's other papers, which are.
Yeah, well, I never made the connection, so thank you for bringing that up. Yeah.
So we have in the series of papers with Wood, we have the notion of probabilistic richness that also takes into account the marginal weight of points which are close to the nearest neighbor. Can you compare these two notions? Are you familiar with it? So we look at the probability that the richness will be violent, which is somehow takes into account a similar consideration.
Right. Yeah, so it'd be interesting to sort of see if one can come up with some sort of bounds both ways, right? Yeah.
When you said in the beginning that you were going to talk about this KNN, I thought you're going to have like a not pretty but precise formula, perhaps. I thought it's going to give like information of what is the right K. Now your question at the end kind of talks about the K going to infinity, which is interesting, you know, from a mathematical perspective, but it's probably not useful algorithmically, right? Because you're not going to take.
Yeah.
So do you have like any insight of what is the right K? I mean, from these kind of like formulas, or?
No. The short answer is no. The honest answer is no. But but the other answer is that, you know, if it falls in this alpha smoothness class, then this is what you would set K to, right? It's just that we have no idea what alpha smoothness class it falls into, if any. Okay, so the answer is no, basically. We don't have any good insight into it.
Okay, thanks. Sanjoy again.